Good morning, everyone. Welcome to this webinar. We're going to talk about in this webinar is the advanced material characterization with Anritsu VNA solutions. Okay, and the third party solution we have. Now, the content of this webinar will be focusing. Just a sec. Uh, Yeah, the content of this webinar will be focusing on the basics of material measurements. We are going to talk about the key parameters like permittivity, permeability, loss tangents. We are also going to talk about different techniques are there in material measurements. We're going to compare the comparison of these different techniques. Then we're going to talk about the system setups and best practices are there to do these kind of measurements. Then in the end section, we are going to talk about the third party integration for special application we have in the global segments, and then the portfolio which supports the Anritsu portfolio which supports these kind of measurements. Okay, starting with material measurement or material characterization. So material characterization is a measurement that is made to characterize or electromagnetic characterization, the dielectric and the magnetic property of a material, simply. Okay, these material properties can be discussed over here are basically permittivity, which is also known as dielectric constant, or electrical property, or permeability, which is a magnetic property. So when we are doing the characterizations of a material in a dielectric domain, electrical domain, or magnetic domain, these properties are called permittivity and permeability. Okay, both these terms, permittivity and permeability, are complex quantity in nature that characterize the way a material is actually interacting with electromagnetic field when it is applied on that particular material. Why it's useful? Because there are different applications where we change the behavior of the components which are used in that particular zone. Okay, starting with permittivity, which is the dielectric constant, also known as, is the ability of a material to store the energy when an external field is applied, or the ability of material to resist that electrical field. Okay, when we do that is basically when a dielectric material is insert in a particular capacitor, let's say for an example, what it do, it basically neutralize the charges, and now the capacitor can can hold more charges or store more charges as compared to the previous. I'll show you in next screen or next slide. Now, its absolute permittivity, which is also denoted by epsilon, is actually the product of relative permittivity and the permittivity of free space, which is a constant, epsilon r and epsilon naught. Okay. Now, this is a small video where we can understand if we are putting a voltage to a capacitor and there is no material in it, or there is a material with dielectric constant of 1, the capacity of a capacitor will be constant, right, to an extent that it can store this much of maximum charges on it. However, if we are going to increase the dielectric constant of the material, or will change the material dielectric, what happened, there will be charge induced on the material which nullify the charges on the plates. Now the capacitor can hold more charges. So we are not doing anything, we are just changing the material inside the capacitor, and we are increasing the capability of a capacitor. So that's how these material properties affects our day-to-day components which are there in our RF domain or electronics domain. Now the second part is that like I said, the permittivity is a complex quantity in nature. That means it will have a real part as well as imaginary part. The real part, which is epsilon r dash, denoted by that, is the measure of the energy, how much an external field is from the external field is stored on the material. Okay, now epsilon r double dash, which is an imaginary part of the complex quantity, is also a loss factor. That means it is a measure of how much energy is dissipated or lossy a material is when it's stored under an external electric field. Okay, now the permittivity is often called as dielectric constant. The name says as a constant. However, we need to remember that these are constant value but for a particular frequency, so it changes with respect to the frequencies as well. Now, if we go into other parameters, there are loss tangent, which is tan delta, also known as. It's a dielectric losses in a material when it's subjected to a alternating electrical field, and indicates basically how much energy is lost or heat in a form of heat compared to the energy stored in a dielectric. Or in other terms, I would say it's a ratio between the energy lost per cycle to the energy stored per cycle, also directly proportional to dissipation factor or inversely proportional to the quality factor of the material. Then we also have we do the measurement of Cole diagram. You might have heard about it. The Cole diagram is a basically graphical representation used in dielectric spectroscope to analyze the frequency dependent behavior on a complex parameter. In this particular graph, what we do is basically we plot the complex permittivity on a single diagram where the imaginary part, which is epsilon r double dash, are plotted on the vertical axis or y-axis, and the real part epsilon r dash is plotted on the horizontal axis or x-axis with respect to frequency as an independent parameter. Now this Cole diagram is very similar to what we have as similar in a Smith chart which we have seen in a VNA. Now, the other part is the magnetic property or permeability, we call it, right? Now, permeability is a measure of the ability of a material to support the formation of magnetic field within itself when it is placed in a magnetic field. That means if I put a material inside a magnetic field, so two scenarios are there. Either there is no change in the magnetic field, or the other thing is that the material itself will induce magnetic field within itself. So that's how it changes with respect to the external magnetic field. Now, in over here, we denote it with the mu, which is mu. Sorry, absolute permeability is again it's a product of relative permeability mu r to the permeability of the free space, which is mu naught. This is again an example where we are putting a free space sample on between the magnetic field. So the magnetic field is there. There is no permeability, so there is no change in the magnetic field as well. However, if we change the material into a low magnetic permeability, again there will be no change in the magnetic field. However, if we change the magnetic permeability to a high magnetic permeability, then there will be induced in the magnetic field inside the material itself, and it will alter the magnetic field which is applied externally. Now, when an electromagnetic field is interact with the material under test with MUT, two parameters are there. One is permittivity and permeability. Like I said, both are complex in nature. That means they will have a real and imaginary part, both real. That means the epsilon r dash and mu r dash represent as a storage of the energy which is stored on that particular electromagnetic field, and epsilon r double dash and mu r double dash, which is the imaginary part, represent as a lossy which is there when the material is kept under the electromagnetic field. Mostly the material are non-magnetic in nature, making permeability very close to the permeability of free space. However, all the other materials, on the other hand, have some dielectric properties attached to it. Okay. Now there are different techniques are there for material characterization. When I say, okay, now what are the different characterizations? So we have open coaxial method, we have resonance cavity method, we have free space method, we have transmission line method, and then we have capacitive methods as well. If we want to broadly classify these techniques, so there are non-resonance based, which include open coaxial, free space, and transmission line, and then we have resonance based, which include resonance cavity and capacitor cavities. Let's discuss one by one these uh, 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 methods one by one. Before that, I would like to ask you guys, if you have any question related to the session we are having, you can drop it the question or queries on the chat box so that we can address after the presentation as well. Okay. Now, starting with the open coaxial method. So it's an open-ended coaxial probe in a cutoff section of a transmission line that is actually submerged or touched the material. So what we do is basically that probe is connected to the material, touch the material, and when it's touching, the material need to be a very flat surface, smooth, or we can immerse this probe into a material. It can be gel, it can be liquid, it can be pellet or powdered. And on the basis of the reflected signal which we are getting on the VNA, which is a vector network analyzer, generally we measure the S11 parameter, and then putting this S11 parameter into the equation of in the software, and we can calculate the electric field or electric property of that material. We can do the characterization of that material. It's a simple setup. However, if we see the setup, this is how the setups basically look like. in which we have a VNA. That VNA is connected, the port of the VNA is connected to the probe, which is immersed on the gel or the liquid of the material. And then we are doing measurement on the software where it's changing the S values, S parameter, the reflected parameters into the required electrical property parameters. Okay, now there are some advantages and disadvantages. Now if I talk about the advantages, first of all, it's very easy to use. The setups look very easy to use. Then it preparation and cleaning is also very easy. We are able to measure solid, liquid, gels kind of materials. They are non-destructive to the material in its test. When I say non-destructive, that means we are not destructing during the measurement. We are not changing the dimension of the material, or we are not changing any specific flow set. It should be it can be a destructive in nature. Along with that, it has a broader frequency range. That means it starts from megahertz, few megahertz, like 4 megahertz can go up to 60, 70 gigahertz. So different models are there. Now, the disadvantage, if I say, of the coaxial probe is that one is that we have to have a large sample size because we need to submerge this probe. So we need to have a large volume of the material. Along with that, solid sample must, like I said, solid sample must have a smooth surface. Then only we will be able to do proper measurement without any error. It's not very suited for extremely low lossy materials, and it has a limited accuracy with respect to their electrical properties or dielectric properties. The second method we have is the resonance cavity method. In the resonance cavity method, it has a high Q structure that is resonating at a particular frequency. So we are aware of the resonant frequency of an empty cavity and the quality factor of that particular cavity. Once we know that, what we do is basically we put the sample inside the cavity, and because of that sample there will be shift in the frequency, resonance frequency and quality factor, and this delta between the resonant frequency and quality factor, we can calculate the material properties. Now typical setups look like VNA, vector network analyzer, along with the resonance cavity fixture and the software that is doing the calculation. This software will note down the shift in the frequency and the quality factor, and that will calculate, or it will tell us the property, the material property based on that. Now again, there are some advantages and disadvantages related to resonant cavity. Now the advantages are it's one of the easiest method to use. Okay, we don't need to do any preparation to do this kind of setup. Just a resonant cavity is there that can be connected to the VNA through a probe, and we can do the measurements. Okay, it has a highest accuracy as compared to other methods. It has a highest accuracy for complex permittivity and loss tangents. It has well suited for low lossy thin film sheets material. There is no calibration here. Like I said, we directly connect the VNA to it, and calibration generally is not required in this kind of setups. And it's reasonably measurement possible with small sample size. So if I have a limitation of sample size, then also we will be able to do the measurement just keeping inside the cavity of the resonator. Now there are some disadvantages associated with resonant cavity. Is that the one and the major disadvantage I'll say is the frequency. So it's not a broadband setups. This setup, either they are working on one particular frequency because it's a resonant frequency, or few frequency points. Then they are not working on the broadband frequencies. Okay, apart from that, the sample size shape is required precise. That means it's a destructive in nature. That means we have to change the dimensions of that sample to accommodate inside the cavity of the resonator. So we are changing the dimension. That's why it's a destructive in nature to the sample. The third we have is free space method. In a free space method, we have what we do basically is there's an antenna that focus the microwave energy onto the material that is parallel to an axis slab sheet of material. This method is non-conducting in nature and can be applied material under test with high temperature or hostile environment. That means in this kind of application where methods where if the user wanted to keep the material under a certain temperature conditions or a hostile environment, then also we can do the measurements. Over here we have focus antenna that is bombarding the that is transmitting and reflecting the signals into the material, and we can see we can measure the material properties. Now, the typical system consists of vector network analyzer along with appropriate free space fixture and a software to calculate the permittivity and permeability. Now, generally, there are two types of configuration in free space transmission. One is beyond the axis, as you can see, the material, the port 1, port 2 focus antennas are focusing on a one axis only. However, there are there are applications where we use NRL arc reflector, in which we bombard the RF energy to an angle to the material, and the reflector is taken out or captured at the other port of the VNA using again the focus antenna. There is a third method as well in a free space, which we call as high temperature free space at high temperature. That means if in case we have to keep the material under test at a certain temperature conditions, then we can put that under a furnace which is a thermally isolated to the temperature. However, these furnace are virtually transparent, or insulation are virtually transparent to the microwave energy, so we can transfer the microwave energy into the furnace to the material without any problem, and we can do our measurements. Now, what are the advantages? Now, first is that it's a non-contacting and non-destructive in nature. That means we are not in the setup, we are not contacting to the material. There is no contact between the material and the setup. The other thing is that we are not changing the dimensions of the material. So it's a non-destructive in nature. The second is it has a high frequency application where we can go up to 100 gigahertz as well. However, the lower limitation of the frequency is limited to the practical size of the sample, then only. Okay, very useful for a material measurement when we have to do at a higher temperature or lower temperature on the negative side. That is also possible using free space. Measurement magnetic material is also possible. That means we can not only do permittivity, but we can do permeability as well using free space method. Now, what are the disadvantages? The main disadvantages is the calibration. There is challenge in calibration for the free space measurement, and that we need to require LRL, LRM kind of techniques for the calibration to do for the setup. Uh, required The other disadvantage is that generally it required a large flat pellet flake samples so that we can kept in between the setup. Now, the fourth we have is this transmission lines. Again, this is also a very simple technique in which what we do is we have a waveguide fixture or a coaxial fixture. In between the waveguide fixture or coaxial fixture, we provide the sample, we put the sample inside it, and based on the reflected signal and transmission signal, we calculate the epsilon values and mu values. That means the permittivity and permeability is calculated on the basis of that. It's an enclosed fixture which is there. Typical setups will be looking like a vector network analyzer along with the coaxial or waveguide transmission line fixture and the software to calculate the permittivity and permeability in that. Now, what is the disadvantage and advantages? The advantage is that both electric field and magnetic field can be measured using transmission line method. It's a simple fixture, so no fancy fixture is there. It's a simple fixture where we have a cross section of a waveguide or a coaxial where we can put the sample. It is generally broadband in frequency. That means start from certain 100 megahertz can go up to 10 gigahertz, adaptable to free space as well. Okay, now what are the disadvantages related to transmission line? The main disadvantage is that the frequency of the lower end limited by the practical sample length. That means the sample length, if the sample length is narrow, then I can't go on a much lower frequency range. There is a limitation on that. Apart from that, precise sample shape is required. Again, it's a destructive. That means if I want to do material measurement using transmission line, I have to alter the dimensions of the sample according to the fixture size and fixture dimension. Then only I will be able to do. So it's a destructive nature. The third point is that it should not have any air gap between the fixture wall and the material. If there is any gap between air gaps or pockets will be there between the fixture wall and the material, then there will be error in the measurement. So you won't have the proper measurements. The fourth one is the limitation of the low loss resolution. So lossy resolution is very limited over here. Now the fifth is the capacitive method or pellet plate method as well. It involves sandwiching between the thin sheet of a material or a liquid between two electrodes of a capacitor. So what we do is basically we keep the material inside the capacitor in the two plates of the capacitor, and based on that we measure the impedance, measure the vector component of the capacitor and the dissipation factor. Both are measured, and we put it into the software program and then calculate the permittivity and the loss engine of that. It's a simple setup as well. However, the limitation, the advantages are that it's relatively simple for computation of electrical property epsilon r using C and D. It's very inexpensive, work well with the thin sheets, PCB boards, films, etc. We can work on that. It has a generic typical accuracy of 1% there. However, the disadvantage is that it is not for a higher frequency. Generally, these methods are used for few megahertz or 100 megahertz max. It does not provide you the magnetic property. So it will just give us the information on the electrical side, not on the magnetic side. Okay, so these were all the 5 methods which are there to do material measurements. Now, before getting into the material measurement, there are some questions which we need to ask ourselves before getting into the methods or selecting a particular method, out of which 3 are very important. First is the frequency range. At what particular frequency we want to work on. The material under test need to be tested on. The other is the expected value of epsilon r and mu r. That means the permittivity and permeability values are there. How accurate we need the system to be. That is the third point. After these 3 important points, we are having properties like how is the material property? Is it homogeneous in nature? Is it isotropic in nature? The form of the material, either it is a liquid, powdered, solid, gel, sheet. Then sample size restriction. Do we have a restriction on the sample size of the material which we are going to do under the testing? Can we go for destructive or non-destructive methods? That means can we change or alter the size or shape of the material or not? Do we need to connect, do the contacting or non-contacting? That means connect the material under test to the setups, or we have to keep it at a non-contacting nature. And the third and the last is the temperature. Do we need to do at a room temperature, or certain temperature or hostile condition is required? Like for example, we have to keep the material testing at 100 degrees Celsius or 1000 degrees Celsius. Then we have to select particular
एक वेबिनार चल
method.
रहा है एक
Okay,
वेबिनार
based on
चल
that.
रहा है 12 बजे
Okay, now this is a graph which actually tells us about the different measurement techniques which we discuss versus the frequency and material losses. So if you see the losses, the coaxial probes have more losses as compared to resonant cavity. Like I said, resonant cavity are more precise and more accurate. The limitation with resonant cavity is that it based on spot frequencies. It is not a broadband systems. So we have cavity for particular bands where particular frequencies where we can do the measurements. Other than that, if we look into the parallel plate capacitor, parallel plate methods, it's basically on the lower side, few megahertz, 100 megahertz. However, if we go for coaxial transmission free space, they are broadband in nature, and we can do that. Now, this is a comparison method, comparison of different techniques which learned so far. Before getting into the next session, I would like to ask you again to provide your valuable questions if you have on the chat box, so that we can address that at the end of the presentation related to uh, this section of the webinar. Okay. Now let's start with, let's go to the third and the final section of this presentation, which is the partner solutions we have and we can offer to our customers and clients. Now, Anritsu partners and solution, not only Anritsu is associated with 1 or 2 global partners, but we have multiple partners in the domain, in this domain, and that is actually covering all the method which we discuss and giving you all the solution, everything which is there, all the 5 methods and the solution. So we are not spraying anything where we are not there. So Anritsu, along with other our OEMs, global partners, we are giving a solution with the complete material measurement setup or profiling. Starting with S212, which is also known as Swiss 212. They are basically Swiss-based company. They are into non-resonance method, specialize in coagulative waveguides, and measure up to 1.1 terahertz of frequencies. Now, they are suitable for solid, soft samples, foam, powder, thin films, dielectric coating, multi-layer materials, and typically their frequency range cover start from 25 gigahertz goes up to terahertz, 1.1 terahertz. Their measurement quantities are permittivity, conductivity, loss tangent, Cole plot, all those they can do with their software. Currently, they don't have permeability solution, but they are working on it. Their R&D team is working on it, and in a few months they might have a solution in the permeability as well. This is how a typical setup of S212 look like, where we have the VNA over here, and the VNA is connected to the coagulative waveguide of the S212, and the sample is there in between this coagulative waveguide, and the software is running on the system where it is calculating our permittivity quantities different. The second partner we have, global partner, is a SPIG. Now, SPIG again, it's a Swiss company where they are based in non-resonance method or open coaxial method. They are specialized and suitable for measuring liquid, semi-solid, gel, pellets, powder, thin films. Their frequency coverage start from 4 megahertz, and they have solution up to 67 gigahertz. Different models are there. So 67 gigahertz till 67, they have solution for that. The measuring quantity include permittivity, conductivity, loss tangent, and Cole plot. Right now, currently they don't support any for the magnetic properties, so permeability is not there with SPIC. Right. However, if you see the typical setup of the SPIC is that you have a DAC TLP setup where they have a coaxial cable and a probe station that is connected to the port of the VNA, and then USB connected to the laptop for VNA and the DAC TLP. The DAC TLP and the VNA do we take the S parameters S11 and S1, and based on that we calculate the permittivity and conductivity of the material. The third partner we have is Keycom. Keycom is basically a Japanese company. They are having both solution in resonant and non-resonant methods. They are specialized in free space, microstrip, open resonators, and they can cover frequency range up to 110 gigahertz. When I say resonance method, they have open resonator, they have strip line type, they have circular disc resonator, they have pellet conductor plates type. So in resonance method, they have variety of portfolio in them with themselves. In resonate methods, they have open mode probe methods. They have S parameter method, which is based on reflection and transmission mode, and then they have something called free space as well. So if you see, the portfolio of Keycom is wide as compared to other OEMs. They have something very unique for material measurement in the magnetic section, where they have this setup, this model, they call it PER01, where they can keep the material under test that can be connected to the Anritsu VNA, and this material is under a strong magnetic field and calculate the permeability of the material. Now, this system is basically very high accurate and specifically for the magnetic property. The fourth partner we have, global partner, is AET. They are based on the resonance methods, specialize in open coaxial resonator and resonation cavity. Measurement of PCB substrate, thin film, low lossy dielectric materials are there. They can cover frequency range up to 40 gigahertz. So they have open coaxial resonator types. They have resonator cavity and dielectric resonators are there. The fifth we have is QWED, global partner, in which they are also working on the resonate method. They are specialized in dielectric resonator that can measure for thin films, cylindrical shape, dielectric ceramics, and low lossy dielectric. They can do that. Their frequency range for dielectric resonator goes up to 15 gigahertz. However, there are Fabry Pero is there, which can cover up to starting from 20 gigahertz goes up to 110 gigahertz dielectric resonators are there. So they have split post dielectric resonator. They have single post dielectric resonator, and they have cylindrical shaped dielectric resonator as well. The sixth, we have a compass technology. Now, the compass technology are working in both. They have resonant base and non-resonance base, specialize in free space and spot beam. That's their specialty, and they have introduced some new measurement techniques as well. Now, the frequency coverage, when I say for compass is that they support up to 90 or 110 gigahertz. This is what they have in free space is focus beam measurement system that is covering up to 90 gigahertz. So if we see over here in the setup, they have focus, they have antenna that is a focus lens, and the energy is focusing on the material that is connected to the VNA. Now the antennas are connected to the VNA over here. Now because of this, the reflection and transmission we are able to do or measure the electrical and magnetic property over here. Similarly, they have introduced something called spot probes instead of using these focus lens which we were using earlier. Now we can use directly these probes that can be directly connected to the VNA, and we can do material measurements or material characterization using them. Again, they have 40 till 40 solutions is there. Now they have introduced something called non-destructive examination as well currently. Now what is that? That means we can keep the material in between these probes, and we don't need to connect or been in contact with the material, and it's a non-destructive examination is there where we can examine the material, or for example a radar dome is there, we can do the material characterization of the radar dome without touching the material under test.
तेरा फोन आ रहा था क्या
this
देखिए.
this is I guess the mic is open. Yeah, so this is an example over here. If you see in this example, that's a very unique example. Over here, we are looking into one port VNA of Anritsu MS46131A that is connected to a spot probe of compass technology. Over here, what we are doing, although we are doing material measurement, but in material measurement, we have an application where we are looking into the thickness of the material under it. So if you see, there is a material of 6 millimeter thickness, below that there is a 2 millimeter thickness, another material is there. So over here we are plotting the thickness of 6 millimeter, and after that if it's detect if there is any change in the thickness, and we can calculate how much thickness is there, and we are able to plot on the graph itself. So this is a very unique application which we cover. The seventh we have is mu epsilon. This is our global partner. They are also working in both resonant and non-resonance method, specializing in coaxial waveguide cavity base. They have suitable for absorbing material, antenna, powder, ceramic, dielectric material, radar domes, gel, resin, laminated shields, liquid soils, low lossy material, and thin films. Okay, their frequency typically works from 500 megahertz, goes up to 60 gigahertz. They have solution till 60 gigahertz, and the measurement parameters they can do is electrical dielectric constants, dissipation factor, lost engine, complex permittivity, complex permeability, electric conductivity, resistivity. All these can be measured using these kind of fixtures using mu epsilon. The eighth and final global partner we have is MMS, which is also known as Microwave Measurement Systems. Now, this system, they are specialized in free space material measurement solution, especially for non-destructive microwave material characterization and material characterization at a certain temperature condition or a hostile environment if required, right? They can cover up to 6 gigahertz, start from 5.8 to 6 gigahertz, and goes up to 110 gigahertz, the solution. So if you see over here, this is a typical set of free space setup look like, where the material is there, and these are the focus antenna that is connected to the VNA, and we are doing the measurement over here. However, sometime we require to put the material under a certain temperature condition. In that case, we use a furnace which is more visible in the next slide. As you can see over here, this is the temperature control furnace, which is going from 25 degrees Celsius goes up to 15 degrees Celsius of the temperature. And these are insulated. So thermally it's insulated. However, if you see this windows, these are practically these are microwave really transparent to the microwave energy or EM energies. So we can transfer the EM waves to the material without any issue or without any problem and do the measurements. Similarly, on the lower side, we have a chambers, lower chambers are there where it can go up to minus 50 degrees Celsius as well, where we can keep the samples and reduce the temperature to the lower side. Now, typically it's start from minus 50 degrees Celsius to 1500 degree Celsius. We can do the measurement, and the frequency range, like I said, it start from 5.8 gigahertz and go up to 110 gigahertz. We can do that. So these were all the partners we had so far with Anritsu. Now these global partners and Anritsu VNA provide a compact and proper solution for the material measurements. So anybody who is looking for any of the resonant cavity base or free space or a transmission line, we have solution along with Anritsu VNA. We have the other OEMs which are global partners are there. They support our VNAs, and we provide a complete comprehensive solution for material characterization. Now, if I talk about the VNA part of Anritsu in the last session, now in the VNA, we are categorizing the VNA in three category. One is our benchtop shockline series. Then we have handle, which is the battery operated. You can take it on the field as well. And then we have some higher performance vector stars VNAs as well. Starting with the shockline series, this is our shockline series, which is benchtop without display. We can display can be connected as a external monitor is there. Starting with we have is MS46121B, which is a one port VNA. Its frequency coverage is 150 kilohertz to 6 gigahertz. It can connect to the laptop with a single USB cable, and we can do the measurement as a one port VNA, and the software runs on the laptop itself. We can do that. Apart from that, we have industry only VNA, which is one port VNA again, but going up to higher frequency. That means MS46131A is a one port VNA, which is starting from 1 megahertz. It has frequency band of 8, 20, and 43.5 gigahertz. So we can go as high as 43.5 gigahertz in a one port configuration. After that, we have two port configuration on the standard, which is MS46122B, which is the gray unit you can see over here. This is the hardware of the VNA. The software runs on the laptop, so it's connect to the laptop using one USB cable. That's it. And its frequency range, again, it's covered from 1 megahertz to 8, 20, and 43.5 gigahertz. After that, we have MS46322B, which includes the controller. That means the PC is inside the VNA itself. So we just need to connect an external display. Now this display can be a touch-based display as well. Again, its frequency starts from 1 megahertz, goes to 8, 20, and 43.5 gigahertz. After that, in the Shockline product line, we have a performance VNA, which we call as MS46522B and 524B. Now, the 2B and 4B are the difference between the two-port configuration or a four-port configuration. So depending on the requirement of the users, we generally suggest that their frequency range, again, it starts from 50 kilohertz and go up to 8.5, 20, and 43.5. So maximum we are getting up to 43.5 gigahertz in the frequency band in the VNA. We have something called E-band VNA as well, which is working on specifically the E-band, which is starting from 55 gigahertz to 92 gigahertz. They are useful for the users who are specifically designing their components and working on or doing R&D in the E-band segments and not on the lower side. So we have something like that. That is connected with the WR12 waveguide as well. Now, after Shockline series, we have a handle series as well. In handle, we have VNA master, we have site master, and we have the new site master. In the VNA master, we having covering frequency range from 500 kilohertz to 4 and 6 gigahertz. And in site master, it's starting from 1 megahertz goes to 8, 14, 20, 30 and 40 gigahertz. So up to 40 gigahertz in a handle formats, we have a solution up to that. Then on the site master side, this is a new addition to the family. It's a new instruments that is covering from 5 kilohertz goes up to 4 and 6 gigahertz for now. Okay, and the product which I am defining over here, they all are compatible with all the 8 global OEMs which we discussed, the partners we have. They are compatible with that. We can do material measurement using any of the product and using their setup and the software. They are compatible with their softwares as well. In the end, we have a vector star, which is a performance VNA from our side. This VNA actually covers starts from 10 megahertz. However, we can go as low as 70 kilohertz and can go up to, we have frequency models like 20 gigahertz, 40, 70. Then we have something called 110, 125, 145, and 220. When I say 220, that means it starts from 70 kilohertz, can go up to 220 gigahertz in a single sweep without any banded, without any breakage. So there is no band, no breakage is there. So it's a single sweep from 70 kilohertz to 220 gigahertz. We have 2-port, 4-port baseband units are there. We have configuration of 2-port or 4-port broadband units are there. And if the user wanted to go beyond 220s to the millimeter wave or terahertz, we have solution to the terahertz as well, or millimeter waves as well. So this is how the family of VNA look likes in from Anritsu side. Now, in the end, I just wanted to address that Anitsu, for the material techniques and material characterization is basically a subject where we use VNA as a heart of the whole setup. Along with that, we use a fixture or the setups and the software which are provided by our global partners. And combining it, we give a comprehensive solution to the material characterization. Okay. Uh, Now, thank you so much for the this presentation and lovely audience. We can address queries related to material measurement or material characterization now. Thank you.